Hello, this lesson is on optimization. Optimization is when you're finding the maximum or minimum values given a function, and we're going to use the derivative to do that. All types of functions, profit functions, revenue functions, average cost function, we're going to use the derivative to find the maximum or minimum. So this function is an upside down opening downward parabola. It's negative x squared plus 10x minus 22, and we talked last unit on how to find the maximum. That was to use the negative b over 2a to find the x coordinate. I do want to mention that on the test, many of you did not actually go through that process. That is the best way to find, before calculus anyway, to find the maximum or minimum given a quadratic, negative b over 2a. But there's a better way, and that is using the derivative. But before we do that, let's just review. So let's say this was a profit function, and this is the graph of the profit function. The question that I wanted to review with you is, where are the break-even points and how do you find them? Well, we know the break-even points are when the profit is zero. So we're neither losing money nor gaining money. That's break-even. And then for a quadratic, there's two of them. So the answer is you find the break-even points by goal seeking this profit function to zero. The original profit function, you goal seek to zero. There's going to be two for a quadratic profit function, and then just want to review how you get Excel to find them both. So it looks like this break even is at when the number of items is 3, and this one is when the number of items is 7. So remember that when you're goal seeking in Excel, you have to give Excel a guess number, and say, Excel, would you please look around the number 3, and then goal seek, and then again say, Excel, would you look around x equals 7, and then goal seek around there. So that's review. And then now the other thing we're going to do is we're going to find the maximum, and this is the best way and the way that you'll use from now on. The old way was to look at the y values for the highest value or use negative b over 2a. But now what we're going to do is we're going to understand that the derivative of a function gives you the slope of a tangent line at any point. And when you have a tangent line through a point and that tangent line is horizontal, that means that its slope is 0, because all horizontal lines have a slope of 0. So that means that if we take this derivative and then goal seek it to 0, we'll find a point where you have a horizontal line. And notice that where you have a horizontal line is where the maximum of this parabola is. So if I draw kind of a tangent line here, you can see it's an increasing tangent. If I draw one here, it's increasing. If I draw one here, and if I keep getting closer and closer to 0, you see it's at the maximum. So the way that we're going to find the maximum is by taking the derivative of the function and then goal seeking that function equal to 0. The x value where that occurs is the number of items that will maximize the profit. And so you won't have to worry about putting in any kind of guess numbers, because you're in this quadratic scenario, you only have one place where there is a maximum. However, what if you have a cubic function, and you had a cubic function in your presentation questions, and so you're still going to be able to do the same thing. If you take the derivative of this profit function and goal seek it to 0, you'll find a nice horizontal line, an x coordinate where there is a horizontal line. But the problem is there could be a horizontal right here, which would give you a maximum at x equal maybe 1.5. But the derivative setting that equal to 0 might give you a horizontal line here, which would be a minimum. So you can see that when you have a cubic function, you have a maximum and a minimum, and the derivative, setting the derivative equal to 0, won't tell you whether it's a maximum or a minimum. So you kind of have to look at a graph, and I like to call it the eyeball method. So if you take a look at your graph, then you'll be able to see where the maximum is, and you can say, hey Excel, look around 1.5 for my maximum. Or if you're looking for a minimum, you might say, hey Excel, look around 3 for my minimum. So the derivative of a function will find the x-coordinate where your tangent line is horizontal if you set it equal to 0, but it won't tell you whether it's a maximum or minimum. So you would need to look at a graph for that. And we're going to look at examples in the lab manual. We're going to do 1, 3, 5, and 8. And just notice that I'm saying that number 7 and 8 are like the project that you're going to have very soon, or that you're working on by now. And so you can kind of pay attention when we do number 8, and then you can finish 1, 2, 4, 7, and 9 for extra practice. Okay, so the first problem in the optimization section, an airline crosses the Atlantic Ocean with a ground speed of X miles per hour. The cost in dollars per person is given by the function C of x equals 100 plus x over 10 plus 36,000 over x, where x is the ground speed. Question A, find C of 500 and interpret its meaning. Question B, find the derivative of C with respect to x when x is 500 and interpret its meaning. And then question C, state the ground speed that will minimize the cost per person. What is the minimum cost? So this function is going to give us a relationship between the miles per hour in ground speed and the cost in dollars per person. And so this first question, find C of 500, means that we're going to plug 500, and this is the input spot, so that's x. So we're going to say 500 miles per hour, plug it in here, and find the cost per person, and we'll use Excel for that. The second one, we need to find the derivative. Okay, so before we can find the derivative, there's a little bit of rewriting we can do here. So if we rewrite C of x as 100 plus 1/10 times x, because there's an understood 1 here, and then 1/10 is the coefficient, plus 36,000 x to the negative 1, we can now take the derivative. So the derivative would be the derivative of 100 is 0, the derivative of 1/10 x is 1/10, and the derivative of 36,000 x to the negative 1 is negative 36,000 x to the negative 2. So now we have this function, and we can then use Excel to plug in C prime of 500, and we'll come back and interpret it. And then the last question is the optimization part. It says state the ground speed that's going to minimize this cost function, the cost per person function. So we're going to go to Excel, and I'll talk more about that when we get there. Okay, so if we want to put in our information in Excel, X is my input, it's miles per hour, and then I'm going to put this cost per person function in, and then I'm going to put the derivative in. And I know I'm going to be evaluating 500, so I'll go ahead and do that, but another part is we've got to figure out a really good domain, so we'll come back and do that. But let's put the function C of x in. Okay. And then we'll put the derivative in. Okay, so we can now answer question A, find C of 500 and interpret its meaning. So 500 we said was miles per hour, and this, if we know the miles per hour, we'll know the cost per person. So according to this, when the speed is 500 miles per hour, the cost per person is $222. So this is just kind of an if then. You use the original function. If you know 500 miles per hour is the speed, then the cost per person is $222. Okay, the next one says find the derivative when x is 500, and so we have that here. And so that means that this is an instantaneous rate of change. The derivative is an instantaneous rate of change. It's not called marginal. It wouldn't make sense to say the 501st mile, so this is an IRC interpretation. So at 500 miles per hour, the function is a cost per person function, is increasing. Not increasing. Usually it is, but look at that. The derivative is negative, so that means you're going to say decreasing at a rate of 0.044, and you take the negative off because you said decreasing, and the units on cost per person is on this derivative is a little tricky. So the y units are dollars per person, so this is a rate of $0.044 per person. That's just the y unit, and then per miles per hour. So the y unit is cost dollars per person, and then the x unit are miles per hour. So at 500 miles per hour, the cost per person is decreasing at a rate of $0.044 per person per mile per hour. And we'll take the s off there. Okay, now the next one is new. It says state the ground speed that will minimize the cost per person. And what is the minimum cost? So what I'm going to do is I want to look at a graph of the cost per person function. So I have to think of a good domain. So x is miles per hour. We know we've been asked about 500. So maybe we'll go from 0 to 600. We might need to go more. Let's go ahead and go to 800. And you can see when x is 0, you have an undefined value. So let's make that a 1 just so there's some values there. And we want to graph, when you're looking at the graph, you're going to graph the input and the original cost per person function. You don't need to graph the derivative. Okay, so you're going to look at the actual graph of the function we're considering here. And I can see by this graph that I have a point at 1 that's really large, and then it gets really low very quickly. So I'm going to actually delete this value and get a better looking graph. And now I can see that this graph is a decreasing graph, and there might be something going on right here. So this tells me I need to work on this domain a little more, and I'm going to take it out to 1100. And if I want these points added to this graph, just click on the graph and you can see that it's graphing up until 800. If you pull these values down, and now it's going to graph more points. And see why that was helpful? Now I can see that there's a minimum somewhere. And the minimum is happening somewhere to the right of 500. Maybe 600 would be a good guess. Okay, so we know visually that the minimum is occurring around 600, but the way we're going to find the minimum is through the use of the derivative. And what's going on here is, if I could find this place where the line was perfectly horizontal, then I could find that minimum. And there is a way to find the place where the line is perfectly horizontal, and that's by taking this derivative and goal seeking this derivative to 0. Okay, now the graph helps me know kind of where it's going to happen, so I'm going to put a guess number in of 600. And what a good guess. I wish I hadn't guessed it that great, but let me just guess it, 550. And then what you would do, usually you won't hit it right off the bat, is you would goal seek this derivative to 0. So data, what if analysis, goal seek. We want the derivative to be 0 by changing the input, and it didn't give us exactly the right answer. It gave us 599.41, and that is going to happen, and that's where WebAssign is going to not be friendly, and it will happen most often in these types of problems. See where this minimum is? It really is flat. There's a large area of just where the values are really close together, making that flat area. So you may have a little bit of error on your WebAssign, and if you feel like that's happening, you can email me, and I can check your work. Or since we've had some emphasis on solving these, what you could do is just algebraically solve 1/10 minus 36,000 x to the negative 2 equals 0, and solve it and get the algebraic answer. That's fine too. But the best answer is 600. Okay, so let's talk about the interpretation. It says state the ground speed that'll minimize the cost per person. This x is the ground speed. So the answer to the ground speed that's minimizing the cost per person is 600 miles per hour. And then what is the minimum cost? It's not the derivative. The derivative gives you the slope of the tangent line. So the original function gives you the minimum cost per person, which is $220. So let me write that out. Okay, so the ground speed that will minimize the cost per person is 600, and then add your units, miles per hour. The minimum cost is $220 per person. Okay, and before we leave this, I did click on the answer key because I have some good discussion here. Again, it says to find the minimum cost per person, goal seek the derivative to 0. This problem is tricky because the graph is horizontal for a long period of time. I put in guess values of 500, 600, and 602 miles per hour, and each time Excel goal seek the derivative to 0 at 598.86 or 600 or 602 miles per hour. So answers will vary on this one, but the best answer is 600 miles per hour. That's what you would get if you were to do it algebraically. And then notice that the cost per person is right on $220 per person each time. Okay, so number 3 says a company can produce no more than 100 items per month, but wants to make at least 20 items. The cost can be modeled by the function C of Q equals 5Q squared plus 100Q plus 20,000, where Q is the number of items produced. And we want to create an average cost function. We want to write the formula for the derivative of the average cost function. And C, we want to find out the quantity that should be produced in order to minimize average cost. So there's our optimization problem right here. Okay, so the first thing you notice is that there's a restriction on what the company can produce. They can produce no more than 100 items and at least 20 items. And Q is my input. Q stands for number of items. So my input is number of items, and they're telling you the domain has to be at least 20 and no more than 100. Okay, so we now know what we're going to be looking at in terms of the input values, and it'll get us a good graph. And this is a graph on what we call a closed interval. And so you want to look for max and mins on these endpoints as well as what the derivative tells us. So again, a graph will answer all questions that we have. Okay, do you remember how to find an average cost function? Well, an average cost function is when you take this total cost function and divide it by the input, which in this case is Q. So our average cost function is going to be C bar of Q equals 5Q squared plus 100Q plus 20,000, all of that over Q. And so we could simplify that, and that would be C bar of Q is equal to 5Q squared divided by Q is 5Q. 100Q divided by Q is 100. 20,000 divided by Q is 20,000 Q to the negative 1. Now we can write the formula for the derivative of the average cost. So that would be the derivative of 5Q is 5, the derivative of 100 is nothing, 0, and the derivative of 20,000 Q to the negative 1 is negative 20,000 Q to the negative 2. And then we're going to say, well, what quantity should be produced in order to minimize average cost? So we are going to graph, not the derivative, but graph C bar and locate the minimum. And we're going to graph it with a domain from 20 to 100. And then to find the minimum, we're going to goal seek the derivative C bar prime of Q to 0. Okay, so when you do these optimization problems, it's important to graph the original function and the derivative, and sometimes even more. So remember, we've got this cost function, and then we built an average cost function, and then we have a derivative of the average cost. And this question's only asking about the minimum average cost, and then it's asking about the average cost per item. So we really only need the average cost function. You don't even need the total cost function. So you have to think about what the question is asking and which function is going to provide you with the information you need. This original function would give you the total cost, and nobody's asking about that. So I'm not going to even graph it. So I'm going to graph C bar, or type in C bar, and I'm going to type in C bar prime of Q, so the derivative. And then this one, we have a given interval from 20 to 100. And I'm going to type in my C bar function. Now, you could make an argument, why don't we type this cost function in and then divide by Q to make it easier? But I just decided to do it this way. So I'm going to type in this average cost function right here. So that's 5 times Q plus 100 plus 20,000 times Q to the negative 1. And then the derivative, C bar, 5 minus 20,000 times Q to the negative 2. So this is the derivative. The derivative is the slope of the tangent line at all of these points. And I want to take a look at my average cost function. So that's what we want to do here, because this is an integral part of kind of finding out where the minimum occurs. And this average cost function also has a minimum that's sort of spread out. Well, it's 1 point, but it just doesn't change very much for a large part of the interval. And this is a fixed interval, so you can see that there is a maximum at 20 items, and there is a minimum here, and this closed interval isn't a minimum. But you have to check these endpoints if you're given a definite domain. Okay, so now we're ready to answer the question, what quantity should be produced in order to minimize average cost? So that's going to happen, again, if you connect the dots here we know a minimum occurs when the tangent line at the minimum is nice and horizontal. So that's why we are going to goal seek the derivative to 0. And also, when you're calculating the domain, this domain was given to you, but you want your derivative to change from negative to positive. And that's how one of the things that you know you've got a good domain. So right here, this is telling me without a graph that between 60 and 70 I have a minimum. I can look at my graph and see that too. So I'm going to pull this down and put a guess number in of about 65, and then I'm going to goal seek this to 0. Goal seek the derivative to 0. We want the slope of the tangent line to be 0. That's what we're doing. And I get it doesn't go completely 0, that's fine. And I get that value. I could try again to see if I can get any closer. I could also solve this algebraically to get the exact answer there. But this would be fine on a test. Okay, so now we're ready to answer this question. What quantity should be produced? So Q is number of items, and let's make sure it's not in hundreds. Nope. And C is cost, so C bar is average cost per item. Okay, so 63.25 items should be produced to minimize average cost. The average cost per item is, this is my derivative, this is my average cost function. So the average cost per item is $732.46 per item. So my average cost units are dollars, because that's what C was, per item, because that's what Q was. But it's not an average rate of change, it just has the same unit. Okay, so number 5 says the annual revenue are in millions of dollars for Chrysler Corporation during the years 1988 to 2000 can be modeled by this revenue function. T is years since 1980. So T is my input, and years since 1980 means that 0 is going to represent 1980. But we have a closed interval here where we're only talking about the years 1988 to 2000. So that would be, if T is years since 1980, that would be the T is 8 to 2000, so that would be to 20. And that's the closed interval that we are going to be looking at. R is in millions of dollars. Okay, so if we write that down, that increases our chances of getting the right units when it's time to interpret. And question A says state the derivative, so we'll just take the derivative of revenue. So that's negative 146.38, and then the derivative of t cubed is 3t squared. So the constant comes down, negative 146.38 times 3t squared plus 6014.19 is a constant. It comes down times the derivative of t squared is 2t minus 75,778.84, and then the derivative of the constant at the end is 0. So there is our revenue derivative. And then it says, question B, using the derivative, when did the minimum revenue occur? And what is the minimum revenue? And question C says, when did the maximum revenue occur? And what is the maximum revenue? So this revenue function is a cubic function. Might remember what that looks like, but we're going to graph it, and you can see that this is an example where you have a minimum and a maximum. Okay, so we're going to put our input in time in years since 1980, and our closed interval, we've already thought it through, is 8 to 20. And if you would like, you might want to insert a column. So if you click on A and insert, you can type in the years that these represent. So this is 1988, and then the second one would be this plus 1. You could just do it that way. You could type them in, but now you have a representation of actual year, and that might help you with your interpretation. This is my input, however. Okay, and we're asked to find the minimum revenue and the maximum revenue. So, and when did the minimum revenue occur? You find the minimum using the derivative. You find what the actual minimum revenue is by using the revenue function. So here's a case where you would have to type in the revenue function and its derivative, and not just because you want a graph. Okay, so we'll type in the revenue function. It's cubic. Lots of decimals, so I'm definitely going to check this before I hit enter. Okay, so I'm just kind of modeling that for you because I don't want you to have any typos. Okay, it looks good. Drag that down, and now we'll type in the revenue derivative. So negative 146.38 times 3 times t to the second power. And we'll check it. So there's the first term, and then second term, and third term. And when we're looking at the derivative, we're going to look for a change from negative to positive. There's a change from negative to positive, so there must be a derivative of 0 equals 0 somewhere here. There's a change from positive to negative. So you can look at the sign change, but the other thing that I like to do is just the eyeball method, which is to insert the graph of revenue, not the derivative, but the original graph. And there is a cubic functions graph, and you can see that there's a minimum and there's a maximum. And this question is asking you for both, but on the test I might ask you for just the maximum. And so you really have to understand this eyeball method, and because the first derivative equal to 0 it's going to find is the minimum. So if you want just the maximum, you're going to have to type a guess number in to get it not to find the minimum first. But this is a problem where we want to know both the minimum and the maximum. So let's do the minimum first, and then we'll do the max. And I'm going to put some test numbers in, or you can look up here and see the sign changes happening from negative to positive derivative. So you're going from a decreasing slope to a positive slope, and somewhere between 9 and 10. So I'll put 10 right here in this place. And this stopped changing values. So let me drag that down. There we go. And then this didn't work because my formula is different. Let me make this the right thing. So if you're counting years since 1980, then the best thing to do is to type in equals 1980 and then plus this value here. And then if we drag this down, it's gonna match up with whatever is over here. So that works. Okay, so we're going to goal seek when x is 10, we're going to goal seek the derivative to 0 because we are trying to find the slope of the tangent line, and we want it to be 0 because we want to find a horizontal line. So that's why we goal seek derivative to 0. So let's do that. And don't forget to click on your input value. It's 10, not 1990. And so when I do that, I get the t value, 9.8, and I also have my year value now that I've fixed this input. So again, to do this the right way, you would say, all right, years since 1980, so you would type in equals 1980 plus whatever the zeroed out year over here is, which is 8. All right, now I need to find the max, so we'll do that. The max occurs when the horizontal line, when there's a line that's horizontal, has a slope of 0. And it looks like it's occurring between 15 and 20, and that's confirmed by this change in positive to negative. So we're going from an increasing slope to a decreasing slope. So my guess number here can be something like 17. And then if I goal seek this to 0, then I get the years, year 1997.57. Okay, so we want to answer this question using the derivative. When did the maximum, the minimum occur, and what is the minimum? So now we have the year, and we have the original revenue function that gives us the amount of revenue right here. So in 1989.82, the minimum revenue occurred, which was, and then again we have to go back to our units. Remember our units, this is in millions, so we can take that value and write the word million out after it, or you can find the actual. This is going to be a large number, so I'm just going to write million. So it would be $30,443 million is our minimum revenue. And then our max revenue occurs in the year 1997. And which was right here, $64,464.85 million. And there you go. So again, if you were not asked for a minimum, you would have had to put a guess value in, or you would have got the minimum. If you don't graph it, you don't know whether you have a minimum or maximum. Although you can think through it here. Decreasing, a negative, this is slope, a negative slope is a decreasing slope. So you know that you are looking at that kind of line and that kind of line. I can't repeat it. But, and then when you get here, a positive derivative means you're looking at this kind of line. And so that's how you know that there's a minimum somewhere in there without looking at a graph. But I think the easiest thing to do is look at a graph, and then you can type in some guess numbers. Okay, so this one is number 8. It's the one that's like the project, and it says you've just opened up a new nightclub, Russ's Techno Pit Stop, but are unsure of how high to set the cover charge, the entrance fee. 1 week, you charge $15 per guest and average 200 guests per night. The next week, you charge $20 per guest and average 150 guests per night. The club will provide 2 free non-alcoholic drinks for each guest, costing the club $3 per head. In addition, the nightly overheads, rent, salaries, dancers, DJ, etc. amount to $1,000. Question A, we have to start there. It says determine the demand price as a function of the number of guests. Now this is really important because I'm telling you to create a function, a demand price P, as a function of the number of guests. What that's saying is that I'm requiring you to let X be my input, and that X is number of guests. And so for this demand price, the P is going to be my dependent variable, and that matters extremely a great deal because you are going to write down ordered pairs, and they have to be in this order even though they are written out of order. It says 1 week you charged $15 per guest and averaged 200 guests, so the ordered pair would be 215 because we've decided, because it said P is a function of X, X is my input. The second ordered pair, it says the next week you charged $20 and averaged 150 guests. So you have to keep track of your input and your output. And then it says the club will provide 2 free non-alcoholic drinks for each guest, costing the club $3 per head. Now I'll go ahead and mention this. This $3 per head means $3 per guest, which means $3 per X. Okay, so we're going to build a profit function, and so remember, for profit we're going to need a revenue function, because profit, and it's going to be P of X is equal to revenue of X minus cost of X. So we're going to need to build a revenue function, build a cost function, and then build a profit function, and then here's our optimization. We're going to find out how many guests are needed to maximize profit, so we're going to need a derivative of profit. And then it says what is the maximum profit, so we're going to use the original P of X function. And then what price must you charge in order to have the number of guests from part 8C. So this one we haven't done before. We're going to need to know the price. I'll talk about that when we get to Excel. And we also want to know the profit with a covered charge of $25. Okay, so this one is a problem where you have to actually build a trend line given 2 ordered pairs in Excel. So we'll do that. Okay, so we have decided, because of the problem, to let the X for number of guests be our input and P for price be our output, and so we created order pairs 215 and 150-20. And there was a problem like this on the test that kind of got some people. So what you want to do is you want to insert a scatter plot, and when you do columns it's going to do it wrong. Okay, so if you switch row column, it'll fix it. Before you assume that it's fixed, what you can do is hover over this point. This point is 150, 20. That's what we wanted. If some of you had hovered over your points, you would have realized that you were graphing something a different point than what you mean there. So it's very common to have to do switch row columns when you do this. Okay, so we have 2 points graphed, and now we can right click and add a trend line, and we want it to be linear. And so I'll put the equation on the chart, and so now we have it, and we'll go ahead and change it to function notation. So our output is P and our input is X, so P of X is equal to 0.1 X plus 35, and that's our demand equation. Okay, so I took the equation that Excel gave me, P of X equals negative 0.15 X plus 35, and I wrote it here, and that's my demand equation. And now I have to determine the profit. Well, to determine the profit, I need revenue. So this is a good review problem, because in order to do revenue is price times quantity, and we want x to stay input, and x is number of guests, so x is the quantity. So that means price needs to go away, and that's a price function. So r of x is equal to negative 0.1x plus 35 times x, which is negative 0.1x squared plus 35x. So I have built my revenue function. My cost function, you're given some information here where you're going to give $3 per guest, some non-alcoholic drinks, and then there's overhead of $1,000. So the cost function would be 1,000 plus 3 times the number of guests, which is x. So profit is going to be revenue, which is negative 0.1x squared plus 35x minus this cost function in parentheses, so I can distribute the negative. So you're going to have 35 minus 3x, which is 32x minus 1,000. And so there's our profit function. Now we want to know how many guests are needed in order to achieve maximum profit. So we have to take this derivative because this is our optimization problem. You can find maximum profit if you take the derivative and set it equal to 0. So we need the derivative here. So let's slide that up. So the derivative is negative 0.1 times 2x plus 32. So we could set that equal to 0 algebraically and find the maximum. I'm going to use Excel to do it. So what is the maximum profit and how many guests are needed? We'll enter those two together. What price must you charge in order to have the number of guests from part 8C? We'll answer that. We'll answer the rest of these with Excel. Okay, so if you read through the problem one more time, see you're looking for how many guests. So we're looking for x to maximize profit. So we're going to need derivative of profit. What is the maximum profit? So we're going to need the original profit function. What price must you charge to have the number of guests from 8C? And what is your profit with a cover charge of 25? So this tells me, again, mind your input. So x is input, but I'm going to go ahead and put my p in, my price in, and I'm going to put profit in, and I'm going to put the derivative of profit in. And I don't need to put revenue or cost in because there's not any questions about it. So now the price is this price demand function right here. So I'm going to put negative 0.1 times x plus 35 in here, and the profit function, we built it, so I'll just type it in. So that's negative 0.1x squared plus 32 times x minus 1,000. That's my profit function. My derivative of my profit function is negative 0.1 times 2 times x plus 32. And so now I just have to figure out some good x values, and x is number of guests, and you have a hint here that sometimes there's 200, sometimes there are 150. So I'm going to count by 50s to start and go to like 300. And again, when I'm looking at do I have a good domain, if you look at your derivative of profit and you see it go from negative to positive, you know you're going to have a max. And so there's a max right here. And again, remember break even. If you go from negative profit to positive profit, you got a break even point here and a break even point here. So this is a pretty good domain, but you know what? Why don't we just graph profit function and take a look at it? And you can see that that's a good domain. We have a nice complete graph where we see both break even points, we see the maximum. So now I can start to answer some of these questions. How many guests needed in order to maximize profit? So to maximize profit, you're going to goal seek the derivative to 0. And I know it's only one place, so I'm not even worried about a guest number. And this would be a very easy one to algebraically solve if you set this equal to 0. But you get how many guests needed? Well, that's 160 guests. And then question D, what is the maximum profit? Well, that's in the original profit function section, and the maximum profit is $1,560. And then question E, what price must you charge in order to have that many guests? And that is right here in our P column. So that would be $19. And then we just have an input question. It says, what is your profit with a cover charge of 25? So X is number of guests. So this is not an input question, as I just said. It's not, because it's X is number of guests. So I can't put 25 in here, right here. That's wrong. That's 25 guests. We want to put 25 right here, but I can't just put 25 here because there's a formula in here. So I have to goal seek. So I'm going to goal seek the P column to 25 by changing the X column, and I get 100 guests, but not so fast. There might be a couple of places where I have 25. So you have to think about that. And okay, so I stopped the video and I thought about that for a little while, and I was thinking was, do I need to have worry about two answers? And the answer to that is no. This x-intercept, this x-axis is x, which is number of guests, and the y-axis is profit. So price is hiding in here so well that I couldn't really think about it. So I just typed in a guest number of like 300 and goal seeked 25, and I still got 100. And by that point, I was pretty sure that we would never ask you something that deep and embedded to see if there were two possible answers, because there's not. So the answer to this question F is what is your profit with a cover charge of $25? And the answer is $1,200. What makes that tricky is because you might think you can put 25 into the input, but you can't. And if it's not the input, you've got to goal seek. So that was tricky because you had to goal seek the price to 25. That whole part is tricky because you have to actually put price in here as the demand function. So you may want to try that again. And before I leave this problem, we could even ask another question. We could say, what are your break-even points? So remember, you would goal seek your profit to 0 because it's right here is a break-even point and right here is a break-even point. So to find the break-even points, you goal seek profit to 0, and you would want to find both of them, and you would want to interpret both of them. Here is a few number of guests in a large cost, and here is a large number of guests in a cheaper cost. So these both these break-even points are significant and something you'd want to think about.